Okay, in this lecture, I want to go through how do we take the abstract grammars and represent them in Scala. So, as you might remember, we came up with this simple grammar, which is the grammar for the natural numbers, right? We have one non-terminal, which we'll call capital N. We have two terminals, z, which represents the zero, and then the successor function. The period is some other n, right? It's a non-terminal. Then a starting symbol is n, which we won't actually use much for the Scala side, but it's always useful to have. Then we have the two rules, right? That n can turn into a z or n can turn into the successor of n. So how do we actually implement this in Scala so that we can manipulate these grammars? Right, well, this is how we're going to do it. And I'm going to go through exactly what each one of these different things is, but we'll also just see how this works, right? So first off, any non-terminal is going to end up as what's called a sealed trait. This is anytime you see the non-terminal, you're going to write it up as a sealed trait with the same name. In Scala, traits and classes all have to start with capital letters, so you're always going to want to make sure that they're capital. Functions can be lowercase, and vals and vars can be lowercase, but we're always going to have capital letters for our case classes and our sealed traits. And then for the terminals, we represent them as case classes. Or we're going to also do a case object, which I'll describe shortly. And these represent the rules that we have, right? So the idea is that we say case object z extends n if we have a rule that says n can turn into z, right? Or can be replaced with z or beget z. Likewise, we have a case class with a successor where the inside is little n of type capital N, which extends n, right? And that's exactly this rule here that n can turn into or can be replaced by the successor of some other n. So we can run this under our Scala kernel, and we get, let's make sure it actually runs. And this should just evaluate so that we can then play with this. Right, there we have a trait, an object, and a class. Again, I'll later in this lecture, I'll talk about exactly what those mean. So why do we want to do this? Well, we can now write down really simple descriptions. I'm going to get rid of all these parentheses. All right, so I can say that, say 1 is equal to the successor of z, right? 2 is the successor of the successor of z. 3 is the successor of the successor of the successor of z. And then we can ask simple questions like, is 1 equal to 2, or is the successor of 2 equal to 3? And if we run this, we see that, well, 1, yeah, turns into the successor of z. 2 is the successor of z. 1 is 1 equal to 2? False, right? Which is what we would expect. And is the successor of 2 equal to 3? And we get true. So this lets us basically interpret our abstract grammar and just be able to play with it as these formal terms, these keywords with things in their parentheses. So how does this actually work? Well, a sealed trait, in Scala, the sealed keyword says that all of the information that you need for this definition is in this file. We don't have to look outside of this file. It's a little bit of like saying private in C++, but we're just going to add it in there. We don't actually need it, but we'll have it in there just for completion. Right, so the idea is that it's sealed. It's everything you need for this is in this file. We're not looking anywhere else in our directory. What is a trait? A trait is an abstract class or a virtual class or basically an API definition. So the idea is that it's a class definition that can't be instantiated. It just tells us how something is. Near the end of the course, when we talk about object-oriented programming, I'll go over exactly how traits differ from classes. But the important part is that you can't actually instantiate it. Right, so for instance, in C or C++, you would typically write something like this, right? A class hello with a virtual void foo, right? We set that equal to 0. The virtual is really the signal that says that this is an abstract class. And then we would implement it by extending the original class, right? And for any of the things that we defined in the abstract class, we actually have to redefine in the implementation, right? We actually have to implement it as opposed to just giving it a name. So in Scala, we can do the same thing. So we can have a trait foo, it has a var in it, my mutable, and it has a function which just has the function signature, right? That it takes in an int and returns an int. There's no definition there. And if we want to actually use something that that has foo's characteristics, then we would make a class, say foo impl, that extends foo, right? And then any of the undefined functions inside, we need to actually give a full definition. For instance, here we'll just make it so that we increment my mutable by 1, and then we add my mutable to n and return that. So let's give this a run. And then, yeah, we can say, well, val h is a new foo impl, and y is, let's say, function important applied 10, and we get that this, compiles. We get 11 for y. We do this again, and we'll still get 11 since we just restarted what h looks like. So how does, okay, so that's what a trait is. A trait is an abstract class that just gives us a formal definition without any implementation. Now, what about a case class? We'll get to case object in a second. But what's a case class? Well, it's a type of class that Scala builds in a bunch of defaults for us in a way that makes what we just did here possible, right? So I can say that 1 equals 2, that the successor of 2 is equal to 3. I can ask these questions and I'll get the sensible answers that I want. And also be able to get print statements that look fairly nice. So let's go through exactly what that case class is. So, right, a normal class in Scala would be something like this, class myCase. It takes in some parameters and maybe has a function, right? And when we define it, we can make some new values, say Q1 and Q2. There'll be 2 new myClasses. And you can see down here that unlike those case classes above, the print string, right, the toString function just prints out this bunch of gobbledygook ammonite.$sesh.command5, right? And this is basically the location in memory that this class object has been stored. Likewise, Q2 has a different location in memory, a different reference point. And when we compare the two, the sort of generic thing Scala does is compares those 2 pointers, and we see that they're obviously 2 different objects, so it returns false. And this isn't really what we want to be doing with case classes. So what do case classes do? Well, we can write the same thing up, but now instead of just class, we write down case, right? Same definition. One thing I want to point out here as an aside is that this is a really useful way to talk about, to put data into strings, right? So you can put in quotes leading with an S, and what it'll do, it'll substitute in anything with $signs for the variable or the value with the same name. So because we already have an X and an N in my case class, I can say $X and $N, and it will turn those into strings and place them into the given string in the right location. That's just a little aside. But so yeah, for case class, same definition as my class, but we've put case class on the front. Now here's a little bit that's different. When I run this, or when I make a new myCase class, I don't have to actually use the new keyword. That's one small difference with case classes. We don't need to use the new keyword. It's because Scala creates a companion object for you automatically that creates this factory method that will spit out a new case class for you if you just call myCase class, period. So that's one small difference. Another difference, as I've already sort of pointed out, is that the toString actually is much more useful. It's basically the name of the case class plus whatever things we passed into it, right? So my case class is equal to my case class X equals hello and equals 10. Much more useful than just the location in memory. And then the last thing, which I also mentioned, is that we can now compare them, and it builds in a automatic comparator that just looks at the parameters that we pass in, right? Hello and 10, and says if those two parameters are the same, then we'll consider these two case classes the same. Otherwise, they're different. Which is a much more useful comparison operator for the sorts of things we'll want to use case classes for. Now, why doesn't this just naturally happen in Scala for normal classes? Well, it's because we don't want to, put in stuff that we don't want. For instance, when we did the class of the rationals in the first homework, we didn't really want to compare them just by comparing the two, the numerator and the denominator, right? Because we wouldn't see that 1/2 is equal to 2/4. So this kind of a comparator wouldn't be very useful. We'd have to still overwrite our own comparator. So it's better that Scala doesn't do anything for us at all, right? We can override it ourselves. So most objects that you want to create that actually have more detail will have more complex ideas of difference or equality, right? Just like we might want to actually print off a bunch of internal parameters as opposed to maybe just the two that are passed in by the arguments of the class. But for something like coming up with an abstract syntax structure, right, an abstract grammar, like we were doing up here, this is really useful. The case class is really useful. So I don't have to have a whole bunch of new keywords floating around. And when I print these out, I get exactly the detail that I want, which is really all about the layered, nested collection of case classes. I didn't talk about case objects yet, right? So we saw that Z is a case object. And this is just a case class of which there can only be one example, right? So I could do this as case class, but then I need to have parentheses on the end. And you can see, I have a type mismatch. I would have to add parentheses into each of these locations. And so this is totally fine, but it's a little clunky for what we want to do because there's just a lot more parentheses floating around. So we can just get rid of these and turn it into a case object. There only exists a single case object in the whole. Let me redo both of those. And it's a lot cleaner. It's a lot closer to what we want. Where's my error here? Oh, I want to change this to case object. There we go. So let's follow these rules now, right? Let's implement these into Scala. So we have two non-terminals, A and B. So we're going to want those as sealed traits. And then we have a whole bunch of terminals, right? So I wrote this up in the whiteboard lecture, and you might notice that there's a single real difference here, right? So we have X, Y, Z, and then we have a Z2. And this is just because as we're making up case classes, we can have two case classes with the same name and different parameters. So we're just going to write this up as two separate instances of Z. Now, in practice, we're not going to have any issues with this because we won't have multiple keywords with the same name. So you won't actually run into this in practice. But it's useful to sort of see that the limitations of the case class world here. All right, so let's start implementing these rules, right? So I see that I have A can be replaced with a Z of A. So I want to make a case class Z A colon capital A extends A. Right. We have case class. With the next one, we have this W, and it takes in an A and a B. So I want to make sure that I have small a colon big A and small b colon big B. And this extends, well, where did the arrow point from? From A. again, like I was mentioning with Z, right? We see X and Y. These don't take any parameters in. So instead of leaving blank parentheses, I'm going to make this into a case object, which extends, this time it extends B, right? Because we have B points to X, and case object Y extends B uh, because we have B can be replaced by Y. And then lastly, right, we have case class Z2 B colon B, which extends A. Let's see if all that compiles. Good, right? And now we can start to come up with more complex sentences in this grammar. Right? For instance, term 1 here can be W of Z2 of Y, comma Y, and we get all of this popping out just as is. You can even notice that the way particularly VS Code here resolves this with the A equals and B equals, you can see what the original non-terminals were that are in those locations. So we know that W has to be an A and a B. Let me see what those were replaced with. Let's see. That's about all I want to show here. Here's an example of the case or of objects. Right. So for instance, here's an object hello. It has val x, a var y, a private val x2, and a function hello that just prints out hello. And the sort of key point here is that I can't say that val h equals new hello. We'll see not found type hello, even though we've instantiated this object. And it's because we can't make new hellos. There's only one that exists, and it was created the moment we created this object. So we can actually reference it directly. We can just say hello dot whatever we want to do from either its member variables or its member functions. So for instance, we can run hello dot hello world, right? And it spits out hello, just like we wanted. So hopefully this gives you a bit of insight into how we're going to be taking those abstract grammars and turning them into Scala, and then we're going to be able to play with this. We'll see next week about case pattern matching and how can we use these case classes to be able to parse through or evaluate a complex sentence in our abstract grammar. All right, see you then.